Okay, with that, I would like to invite our next early career research scientist, Ms. Caitlin Greenland Bews from Liverpool School of Tropical Medicine. And she will talk about application of HRM variant calling for monitoring of SARS-CoV-2 variants. So Caitlin, we are very happy that you're here with us.
Of course.
And the floor is yours.
Cool. So you can all hear me? Yeah. So yeah, as Nisha said, I'm Caitlin Greenland Bews and I'm a second year PhD student from Liverpool. And I'm excited to talk to you today about HRM development for surveillance of SARS-CoV-2 variants of concern. So this is probably the last room in the world that I'd have to explain what a SARS-CoV-2 variant is, but I'm going to do it anyway to provide a bit of context. So yeah, the variants of concern emerged towards the end of 2020, with alpha, beta, and gamma being the first being detected. And the term variant of concern has been used to distinguish variants that demonstrated increased transmissibility, detrimental changes in epidemiology, increased virulence, or a decrease in effectiveness of public health measures. And these variants were obviously largely detected through sequencing and monitoring these genetic changes as the virus was evolving. And this was used to make important public health decisions. However, the problem that we were facing is many regions had limited access to sequencing technologies, as it's still very expensive and many regions lack the infrastructure, which resulted in there being a surveillance gap, with most surveillance data coming from higher income geographies. So here, just to illustrate this point, is a map on the left-hand side of the slide showing the public availability of variant of concern sequences as of October 2021, with the grey regions demonstrating where there was no data available of variant of concern sequences. So although infrastructure and investment has definitely been increasing and improving since the pandemic to improve sequencing availability, there are still many countries that rely on outsourcing their sequencing to other countries, which results in a delay in receiving that important data. So what we need in the interim is a cost-accessible technology for molecular surveillance, such as targeted mutation detection with molecular diagnostics, such as high-resolution meta-analysis, or HRM. So firstly, or actually is HRM. So HRM is a post-PCR analysis method, which is very sensitive to nucleic acid sequences and changes in those sequences, which makes it perfect for detecting SNP mutations found in SARS-CoV-2. And how it works is you design your primers to target your regions of interest, and then you use PCR to amplify these regions. And then using an intercalating dye that fluoresces when in the presence of double-stranded DNA, we can melt the temperature from around 55 degrees to 95 degrees. And we can see that as the concentration of double-stranded DNA goes down, as they're melting apart, the fluorescence also goes down. And then we get a readout that you see on the left-hand side of the slide here. And we take the negative derivative of this to give the peaks on the right-hand side. And the positions of these curves, or the melting temperatures, are influenced heavily by amplicon size and nucleotide compositions, and therefore we can use this to differentiate between the different DNA targets. And the benefit of this technology is it is very high multiplexing, it's so much cheaper and faster than many sequencing technologies, and it is also very easily updatable. So we wanted to design an assay that would be able to identify the different variants of concern that were circulating. So first we had to identify what targets we needed to be able to differentiate between them. Luckily for us, there was a lot of sequencing data available when we first started. So just shown on the left-hand side here is a screenshot of the database covariance.org, which gives you a very graphical representation of what SNPs were present in which mutations, which we used initially to just narrow down which targets we wanted to use. And then we'd identify these in a multiple sequence alignment shown here, just to make sure that these mutations weren't found in any other minor variants, and we were only targeting each variant independently. And as we only wanted to know when the mutation was there, we designed our primers so the 3' end of the forward primer would sit on that SNP. So if the SNP is not present, there would be no amplification and you would get no peak. And once we've done some optimization, this is what our final multiplex looks like. So these lines you can see on the screen are showing the different readouts for different variants of concern, as well as a wild type. So we ended up having 4 targets in the end in the final multiplex. We had A570D for alpha, and that's just shown here with the purple line that amplifies at around 80 to 80.5 degrees. And then we have the L452R mutation targeted in delta, which is the yellow line, which shows a double peak between 79.5 degrees and about 81 degrees. And we can use this double peak to differentiate between alpha and delta. As you may notice, they amplify at about the same temperature. Black and red lines are representing beta and gamma, and we did not target those variants in this assay. So they only show this peak on the far right-hand side, which is just used to show that the assay is working. It's used as a control peak. And then finally, to target Omicron, BA1, we used the EP214 insertion in the spike protein, which amplifies at around 78 degrees, and that's that kind of dark blue line at that temperature. So we had our assay and we wanted to test it on clinical samples to make sure it was working. And we were very grateful to be part of the Malkov study, which stands for malaria as a risk factor of COVID-19. And this was conducting a sample collection in Western Kenya and Burkina Faso. And for our evaluation, we used SARS-CoV-2 positive nasopharyngeal swabs that were collected between March, April of 2021 up to February of 2022. And what we did is we sequenced 199 samples collected between these two sites using the Arctic protocol on the Oxford Nanopore MinION. And then we also analyzed these 199 samples with the HRM. And the sensitivity and specificity of the assay was determined by comparing the two results between the assay and the sequencing output. So this is the first set of data we got back from the Burkina Faso samples. So the panel on the top is showing the variants detected by sequencing from Burkina Faso. So this is 112 samples collected between July of 2021 and January of 2022. So this is primarily Delta samples, 21I and 21J, with a few Omicron samples in there as well. And on the bottom panel, you can see the variants that are identified for the same sample set by HRM. And although the HRM cannot detect the subvariants of Delta, you can see just visually that it mimics quite closely the distribution of variants, with just a few negative and undetermined results with the HRM. And this is the data from the Kenya cohort. So this is a bit fresher. I got the sequencing results back about 2 weeks ago for this. The top panel is the sequencing results again. And we had samples from March of 2021 to February of 2022, which meant we got a really nice distribution of alpha, delta, and Omicron samples, which was great for the evaluation. And we also saw an ETA sample and some 19B in there as well. And then again on the bottom panel, we've got the HRM results, and largely mirrors it again. However, we did see more undetermined results with the HRM than we did with the Burkina Faso sample set, which means that the HRM produced the control peak, but there were no signature peaks, allowing us to identify the variant of concern. And then this is the sense and spec analysis for each target, and this is combined across Burkina Faso and Kenya. So all targets had a specificity of 100%, and sensitivity was between 88 and 89% for each target. So overall, we've shown that we can identify variants of concern with a relatively high sensitivity to sequencing. HRM is a good method that provides a low-cost, accessible method for identifying SARS-CoV-2 variants of concerns. It's very flexible and easily updatable. For example, when we first started developing this assay, Omicron emerged, and within about 2 to 3 weeks, we could design and incorporate into the multiplex primers that could detect Omicron. It's also very flexible to other pathogens. You could apply it to other pathogens of interest. You might not want to track variants of concern forever, but you could target your own pathogens that are interesting. The main limitation is you are still relying on sequencing data to design your primers. So this is not designed to replace sequencing, just to support any sequencing infrastructure that may be existing. So thank you all for listening, and thank you to all my collaborators and to the UK ICN for funding my travel to present this work here.
Thank you very much, Caitlin. Nice work. Do we have any questions? In between, I can ask just a short question. Did you observe in any samples like double peaks that would, when there was a time that the variants were mixing? So did you see in any samples that would look like like a double infection or something like that?
No, that's what we'd hope we'd see if we were able to test like a full set. That was just for 93 Kenyan samples, but I've also run the assay on about 600 that have not been analyzed yet. But I'm kind of hoping with that data set, I might see more of a kind of
that
evolution.
might seem interesting, right? Yeah. Okay.
Thanks. So my understanding from your investigation is that you need to have something sequenced so that you can start to look for which parts are going to be identified. Have you been able to take forward your theory to identify whether there's a chance to use this HRM to identify new variants without having a sequence available? So is there any way to look and see at what particular temperature there's regularly a response to identify whether there's a new one before we get samples to a sequencer?
We've not yet. No, that is kind of the dream with this assay, because like you said, the limitation is we need the sequencing data. You can see shifts if there is a mutation in that primer region. So these primers are quite specific to where I wanted the mutation to be, but you can also design it more broadly. So if you know there's maybe a variable region, you could target your primers to amplify that. And depending on how it shifts either to the left or to the right, you could potentially use that as an indicator, but it wouldn't necessarily give you very specific information. You would just see that there was mutations happening.
So it would be potentially useful extrapolation in the field to help people identify where samples should be prioritized to sequencing.
Yeah, exactly. So any samples that were either negative or, like I showed there, unidentifiable, they would be prioritized for sequencing if possible.
Okay, if there's no more questions, thank you, Caitlin.